So today we're going to talk about slope fields, which is one of the few topics we have to make sure we get to before we end this whole game of finishing the BC curriculum. And this one here is just a basic example of something you probably already can know how to do, but I just want to kind of show you a basic idea of what a slope field represents and what you use it for. So over here, what I've given you is a grid. This is an XY grid. I know it doesn't look like one because there's all these dots, but I just kind of put dots at the points, the key vertices. So this is an XY grid. And this point here is 1, 1. This point's 2, 1. This would be 2, 2, 3, 3, 3, 4 here. So we have a set of 16. And if we kind of put these points, I could put these points here, right, on the axis as well, because they're going to become very relevant too. So we have all these different points at the vertices. So we have what looks like something in the area of 81 points or something like that. And this is, far more than you'd ever be asked to do as far as creating one of these slope fields. But what a slope field does is says, when you have a differential equation, this is a differential equation. It's a differential equation because it has a differential in the equation, dy dx equals negative x over y. So this is a differential equation, and you had to solve this. The question is, could you solve this? Well, this is something we can actually solve. But sometimes we're going to have differential equations that we can't solve. And the question is, when we have a differential equation, can we come up with some representation of what that function would look like? The answer is yes, because we know that dy dx represents the slope. So since it represents the slope, we can use that information to figure out what the slope would be at a whole bunch of points. So let's think about the point 1, 1. At the point 1, 1, right, when it's x and y are 1, 1, 1, what would the slope be? Well, the slope would be negative 1 over 1, right? At 1, 1, the slope would be negative 1 over 1. So that slope would look like, downwards, that ratio like that, kind of like that. It's really hard for me to write with this thing. I'll try it again. So that's like a negative 1 slope. Now, what about 2, 2? What would the slope be there too? Well, at that, it would also be negative 1. Negative 1 here too. And in fact, at negative 1, negative 1, it's going to have a negative 1 slope. So at all these different points, so we're saying we don't know what this equation looks like. We don't know what this graph looks like, but we know that if this curve went through 1, 1, it would have a negative 1 slope. If the curve went through 2, 2, it would have a negative 1 slope. And we just don't know, what it would look like, but we know it would have that slope if it went through that point. Now, what if it went through the point 1, negative 1? What if it was down here? What would the slope be at? Well, 1, negative 1 is going to be negative 1 over negative 1. It's going to have a positive 1 slope. What about a 2, negative 2? If it went through 2, negative 2, it would have a positive 1 slope. So we're just noticing that if this curve went through these points, this is what the slope would look like at those points. And that's what you're doing when you're doing a slope field. You're kind of saying, if this differential equation, we don't know where it goes through, right? Because we don't know the constant, we don't know the particular solution. Remember, when we have differential equations, we only have general solutions for them unless we have some kind of constant or some kind of point that allows us to kind of define the particular solution. So we're just coming up with all these options, all these possibilities that if it goes through this curve, what would the slope look like? Now, what if we went out here to, let's look at the point 2, 4. At 2, 4, we're right up here now, right? At 2, 4, we're going to have negative 2 over 4. I think that's negative 1/2. So it's going to look like this, right? It's not going to look a little flatter, right? It's a little flatter than the previous ones. So it's going to have a negative slope, but it's going to be flat because it's a negative 1/2 slope. And if the curve went through 4, 2, right? If we went to 4, 2, what would the slope be? Well, at 4, 2, it would be negative 4 over 2. So it's going to have a negative 2 slope. So it's going to be steeper. So we can keep on looking at all these points and kind of start drawing at all the points, at each individual point. If it went through that point, if this curve connected to that point, what would the slope be? Okay, we can say over here, it's going to be negative 2, negative 3, negative 4. That's really steep. Over here, I think it's going to be negative 1/2, negative 1/3, negative 1/4. You can see that these get hard to differentiate the two. So what I'm going to do is I'm going to fill this out. I'll be back in a second. Okay, so we have a whole bunch of slopes that entered in here. And if you look, what I did is I kind of have horizontal slopes here and vertical slopes here. You may say, well, why do I have horizontal and vertical slopes? The reason I have horizontal and vertical slopes is because if you plug in x is 0, right, which is what's happening along the y-axis, you have 0 over some number. So it'd be the slope of 0. That's a 0 slope. These are all 0 slopes here, right, folks? So what about what happens along the x-axis? Well, along the x-axis, y equals 0. And we know that we have a number over 0. We have a vertical slope. And a vertical slope is what I'm trying to depict here. So now we have all these possible slopes for in the event that if the curve went through 4, 2, the slope would be -2 there. If it went through 4, 3, it'd be -4/3 there. And what we play when we're doing a slope field is we're trying playing connect the dots. And what I mean by connect the dots is I want to say, let's pick a point. And I'm going to pick 5, 0 because just I have reasons and you'll see soon. But that 5, 0 there has a vertical slope. And if I were to try and go around this, I would start to go up. But the second I start going up, right, I'm going to have a slope that's going to be very steep but negative, right? Imagine like -5, 0.1, right? At -5, 0.1, I'm now at a negative slope of like -5,000 or something like that. -50. But as I get further up, I'm going to start to level off. And I may, now I'm at a negative slope here, and now I'm at a negative slope of -4/3. And right here, I'm at like a slope of -1. And now I'm going to start to level off. Now I'm at that -3/4. I'm just kind of leveling off here. The slope's just getting harder to do on the surface than I thought. So now, as I'm now hitting this point here, I'm now going to slope up positive, right? Now we're positive slopes, but it's really shallow. And it's really shallow, but as I move along, and I'm getting further in the x, it gets steeper and steeper. And this should go through here. It's getting steeper and steeper and steeper. Okay. And now I'm going to come around. So I'm imagining there's a point. Every one of these points, I'm imagining that there's a point. Okay, I'm following along here. As I'm getting close to here, I'm getting almost to 0. Here I hit 0. And now, like, I'm at what, I'm at 0, -5. Well, imagine I'm now at 0.1. Coming like -4.9 or something like that. Well, it gets really, really shallow. It's like a 1/50th slope or something like that, right? But it's going to work its way to being a higher number because that ratio is going to keep changing. And I'm taking too long to show this. Okay, so now what do we have? Well, we have a circle. Yeah, that's a perfect circle. And in fact, that's what this slope field is telling you. The slope field is telling you that this is a perfect circle. And it doesn't tell you, what if you started here? Well, if you started here, you would have gone around too, right? If you would have started here, you would have gone around. And you would have hit a different circle. And if you would have started here, you would have had a different circle. And these are all the possible circles that could have been created by this differential equation. Now, we know how to solve this differential equation. We've done this one before, right? We've solved this. We may not have done this exact one before, but I think we have, right? Oops, this could be dx. So this is the differential equation that we have. We've solved this. Well, I'll take a second. I'll take the 2 steps to. Why can we solve this? Because of what we're able to do right here. We were able to separate the variables. Notice how we separated the variables, and that's what we do with differential equations, right? We separate the variables, and that allows us to solve it. Let me put that negative in there, and now we're going to get 1/2 x squared plus 1/2 y squared equals c. Now, if I multiply by 2, I'm going to get some different c, obviously. But that c, call that 2c, is also an r squared, right? Because this is the equation of a circle. And that makes sense, right? This is the graph of these circles. It's like, and you may say to yourself, well, why are all these different circles? How do we know the r is? Well, yeah, that's what this is, right? This constant is effectively telling you, oh yeah, this is a different constant. Maybe that was 11, maybe it was 15, maybe it's 25. We don't know what this constant was, but this constant is related to the radius. Okay, this constant is related to the radius because that's why we have different circles. If this constant was 1/2, then this would have been 1, and that would have been this little circle here. If this c happened to be, for some reason, 5/2, right? 25/2. But see, if this 25/2, it was 12.5. When you plugged it in here, you got 25, and that's why you get a radius of 5. If you had a radius of 5, that's this first circle I drew. That's the wide one. That's R5, and that's why I went through the points 3, 4, 3, and 3, 4. And that's why I chose that one, because it's ones that we know goes through 3, 4, 5 circles and stuff like that. So, okay, great. So you're telling me the slope field thing, why are we doing this? Well, this is a fantastic thing, but this is far better, right? This is far better. I would rather have this than have some graphing connect the dots game, right? But the reason why we have to do differential equations is sometimes we're asked to do something where we cannot. Look at this, x plus y. Okay, so you say, well, I want to do the green method because the green method is better. And I'm going to try and separate the variables. So I'm going to subtract y from both sides. I can do that, right? dy dx, subtract y. I can do that, right? I want to get all the y's to one side, all the x's to the other. Now multiply both sides by dx. And I get negative y dx, because I have to multiply everything by dx. And here's where you get a little frowny face. Because you notice that there's no way to not connect that negative y and that dx. That y and x, that y and that dx can never be separated. They're always going to be together. They can't be separated. So this is a non-separable differential equation. Now, you will never be asked to solve a non-separable differential equation in BC Calculus because solving equations where it's not separable, that's for a whole other course. That's for a next level of calculus. That's for Calculus 3, or where there's full courses in college called differential equations that you could take where you're just solving differential equations. So that's something we can't solve. Therefore, we don't have the ability for us to just come up with this beautiful equation. At least you don't have this ability in this class to do that. But we can kind of depict what it would look like graphically. And that's what we do with slope fields. We plug in points. So we can say to ourselves, well, what at the point 1, 1? What would the slope be? Well, the slope would be 2, right? 1 plus 1 is 2. Well, what would it be at 2, 1? Well, 2 plus 1 is 3. And what would it be at 4? It gets really steep. It almost looks vertical. It's really hard to see the differences there, right? It's so vertical. Just make sure it's positive still. All right, well, that's great. What about over here? Well, negative 1, 1, if I plug in negative 1 plus 1, I get 0. Well, what about at negative 2, 1? Well, negative 2 plus 1 is negative 1. Huh. So we can start seeing, some patterns. And I'm just using across this, all these points where y equals 1 here just to start to show you the trend. But now let's do it at, we can do it at the zeros, but we'll just do it at the 2's. Think about it, negative 1, 2, we still have a positive slope. At negative 2, 2, we have a 0 slope. And then here we have that negative 1 slope. And what you're going to see is that kind of everything along these diagonal, these negative y equals negative x diagonals are going to be the same. If you plugged in 0, 0, you'll get a 0 slope. If you plugged in 1, negative 1, you get a 0 slope. And all these are going to have a 0 slope. And all the ones along this diagonal right here are going to have a positive 1 slope. And you could finish it all up, which I'll do. Okay, so you'll start to see that, differentiating between a slope of negative 1/8 and negative 1/7, it gets really hard to do. So you're not expected to do that. It's going to look flat, right? Negative 1/8, negative 1/7 down here in this bottom left corner, they're going to look the same. Like this 8 and the 7, they're going to look the same. They're going to be really, really steep. They're almost going to look vertical. And they're not going to ask you for that kind of, close, idea of like exactly what it's going to look like, but they are going to want you to kind of see what the trends are. And they might say, hey, if this went through, say it went through 1, negative 1. If it went through that, they may ask you, what would it look like? And you're going to have to get an idea for, well, what would happen? And this is what we have to do with differential equations. We have to figure out what would happen. If we were at negative 1, 1, it's vertical here. Horizontal. It's horizontal here. So as I go over here, it's going to start to go up, right? It's going to start to go up. Now, how fast? Well, I don't know exactly how fast it's going to go, but if I was in the point 1, negative 1, when I start moving to the right, it's going to get to positive and then a little bit, also negative 1. So it's going to be slowly start to go up. And it's going to eventually wake its way up. And I don't know how fast. And you might go over here, might go over here. I can't know that, but I can know that it's going to start to follow a trend like this where it's getting steeper. Now what's going to happen over here? Well, as I go over here, it's kind of going to be a little bit weird, right? Because it's going to start to move up. because if you think about this, it's going to start to move up, but it's not going to move up that much because as I'm moving up, I'm kind of canceling it out. So I don't know exactly what it's going to look like, but I'm guessing it's going to look a little bit like that, right? It's not going to ever, actually, it shouldn't hit that point here. So let me undo that because it should never get back to being flat again. But the second it starts getting too shallow, oh, maybe that's wrong. Yeah, maybe that's wrong. See, I don't think it's going to tail up there at the end. My guess is that, I think it would probably look, I think it would approach like -1 slope. That makes sense to me. Because as it's going up and to the left, it's kind of almost approaching a line, I would think. But I mean, and you're not supposed to know exactly. You just need to know that if you kind of get too shallow over here, right? If you were down here, right? I just would say if you were down here, as you're going out, you're going to curve up, right? Because it's going to want to curve up a little bit more. As you get further up here, it gets more curved up toward -1, right? So it's going to curve up toward -1, and that's the idea that you want to get. That's going to be kind of getting that overall bow shape. But that's all you're asked to do in slope fields. All you're asked to do in slope fields is use some usually non-separable differential equation. And usually what you're supposed to do with that non-separable differential equation is you're able to kind of figure out, oh, okay, if this is a non-separable differential equation, well, what's the trend going to look like? And you do that by plotting points and then seeing how it's going to connect. They will sometimes give you a slope field and ask you to interpret it. Other times they will ask you to create a slope field. And this is something that you can do because it's a way to kind of think about and analyze non-separable differential equations. And that's the value of a slope field.